Good afternoon, everyone. Welcome to this session. As you all know, this is the live session conducted for NPTEL course Solid State Physics. Course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I am Mrinalini, PMRF Research Scholar from School of Physics, University of Hyderabad. So these sessions, as you all know, is conducted every Saturday 3 to 5 p.m. where we discuss that particular week's topic, small revision, and if any of you have doubt, you can ask. And mainly we focus on doing some numerical problems related to that week's topic so that it will help you in solving your assignments for that week and ultimately will help you take your exam at the end of this course. Okay, so first let's have a quick uh, glance of what were the topics that were discussed last time. So last week we had discussed about semiconductors, very important type of material these are. And so like we know in this also we had discussed that we have different kind of materials in solids. If we talk one that we say metals which have high conductivity that and small resistivity, then we have insulators which we say are poor conductors, sorry, not metals, I mean conductors. Mostly metals constitute conductors, and then we have insulators, and in between this we have materials called semiconductors whose property like conductivity or resistivity lies in between that of conductors and insulators. Then we had seen how we have different type of semiconductors like intrinsic and extrinsic. And intrinsic semiconductors, when we dope with acceptor atoms or donor atoms, that is group 13 and group 15 atoms respectively, and then we get some impurity induced in the intrinsic, and when we dope, that is adding holes or extra electrons in the intrinsic, then it becomes extrinsic semiconductor. So these were the things we had discussed, and which are the atoms group in the periodic table which constitute acceptor atoms and donor atoms, and thus they give extra electrons or extra holes. Then we had discussed about the concept of effective mass of electron. Usually the mass of electron that we have been discussing before that, we used to take the mass of electron to be 9.1 times 10 to the power minus 31 kg. But we, after discussing this in semiconductor topic and seeing that when electron passes through in a solid where of course the electrons, valence electrons, are free to roam around and they are not bound to particular atom, but still they are inside the solid, they are not free to go out of the solid completely. And this kind of situation shows that because of the interaction of electron with the lattice, crystal lattice, there is sort of interaction that leads to change in effective mass of electron. So as a result of the interaction between those free roaming electrons inside the particular solid or that body and the lattice atoms or ions, there is some change, and thus the electron's mass can become positive or negative depending on the wave vector. And so there is, this concept of effective mass got introduced to us. Then there was another concept of Hall voltage, that when there is any kind of material and we apply voltage to it, that leads to flow of current, and perpendicular to the flow of current, if we apply magnetic field, a static or constant DC magnetic field, then perpendicular to both the direction of current and magnetic field, like say if the current is in x direction and this is x direction, let's say this is y direction and up is z direction, then x direction the current is flowing and z direction we have applied magnetic field, then perpendicular to both of these two directions, that is the y direction, we'll get Hall voltage. This is happening because when the charge, electron and holes, whichever we consider, is flowing, because of magnetic field there is a force they experience and the direction of that force is along y direction, because velocity of charge is in x direction, magnetic field is in z direction, so cross product will be in y direction, and then depends on if we are considering electron or hole, so they will go in opposite direction and kind of accumulate on these walls. And thus if we connect a voltmeter, then we will see there is voltage difference because of this positive charge accumulating this side and negative charge accumulating this side. So this is the origin of Hall voltage, and this is the concept of Hall effect that we use in some experiments to find out if we have a semiconductor and we do this, if Hall voltage, using Hall voltage, if we can find out the hole density or charge density, and then we have had formula, this Hall voltage formula. B is the magnetic field, I is the current, N is the carrier density, D is the thickness of the sample, and Q is the charge. So if we get, out of fitting everything else, if we get it negative, means the electron is the majority carrier here. If it's positive, that means hole is the majority carrier. So this, and furthermore, use of this Hall voltage experiment is there. Another thing we had seen how 4 probes helps us getting error-free resistance for a sample, especially when a sample has very small value of resistivity like metals or some semiconductors, and thus 2 probes may result in a lot of error in the value, whereas 4 probes help us eradicate this situation. So here what we do, we put all these in a linear, in a straight line, equidistant, and outside these 2 probes we are supplying current, whereas we are taking voltage from the inner 2 probes. Thus there is, whatever the current is flowing in the outside wire, because this wire will also have some resistance. So if in 2 probes, when we were taking the current and voltage with the same wire, and we used to just apply and the same connection, so we were getting the resistance of the wire also. So voltage drop was because of that also. But when I'm separating my current supplying wire and this another source, 2 probes I'm taking for voltmeter, then here what is happening, voltmeter, because it has very infinite impedance, we can say infinite resistance, so no current is flowing in this, so no, or even if I'm using wire, the current will not flow in this, and thus it's not drawing any current. So whatever resistance is there of the material, that true value it will be able to give us, and then we can calculate the resistivity. First, like we know V is equal to IR, so we will be able to calculate resistance, and then we know resistance is rho L by A. From this relation, we can find out resistivity of the sample. So it will help us get to the true value and eradicate the error or the extra resistance happening due to the contact resistance or the wire's resistance. So that's how the 4 probe method of finding resistivity for particular samples is very useful. These were the things we had discussed, and then we had done some problems related to this. Now this was related to the electrical properties of solids. Now we can move on to understanding another important aspects or related properties of solids, which is thermal properties of solids. So electrical, we were seeing how when electrons flow or we apply voltage and electrons are flowing, then resistivity, conductivity, these properties is what we were paying attention to. How current is changing, voltage, what's happening to voltage, some other voltages coming into picture when we are applying a perpendicular magnetic field. So these were the properties we were checking. Now when we go to thermal properties of solids, we want to see how to any particular solid material, when I'm applying heat in any form, that could be any way, but if I'm applying heat or energy, supplying energy, then how its properties change. So one important thing that was studied was specific heat. So by definition, specific heat for any material, it is defined as amount of energy or amount of heat required to raise the temperature of that material by 1 degree centigrade for unit mass of material. Like how much energy is required, say if it is some T degree centigrade, this material is, and to increase this temperature to T plus 1 degree centigrade per unit mass, not the whole body, I'm talking like per unit mass, like we define density, right? It is mass per unit volume, so it's like always same. The specific heat is also a characteristic of a material. Of course it depends on temperature, but it's also characteristic of material because we are talking about per unit mass. So that means if I have 1 kg of some same sample and the amount of energy required to raise its temperature by 1 degree centigrade is something, then if I have 10 kg of same amount, then to increase it's same sample, but to increase, because now it's 10 kg, so the amount of energy required to increase its temperature again by 1 degree centigrade will be more because the mass is more, the amount is more. So usually we define it by for defining specific heat capacity, we define it as it is the amount of energy required by that material to increase 1 degree centigrade per unit mass of that substance. That is how we are defining it. So the thing is, this was studied, and then experimentally when specific heat, which is given by the change in energy, I mean the amount of energy found with respect to du by dt. So it was seen experimentally, if we plot increase with temperature, how the CV is changing, then it was seen something like this. After some time it becomes constant, the specific heat, and it becomes 3R, where R is the constant, gas constant. So it becomes constant. This was experimentally seen. But to understand why this is happening, there are 3 models or 3 laws or 3 theories that were given, and we'll see what were those 3. So first model to explain the specific heat capacity for any solid, it was Dulong-Pettit law. These were 2 scientists, Dulong-Pettit law or Dulong-Pettit model. What it explained is, it took that, according to this model claimed that heat capacity is independent of temperature, and it only depends on number of molecules or atoms in that body. This is the claim, and derivation you can check in the lecture video for this week, so I'm skipping the derivations. But what mainly it talked about, it was taking that it only depends, the specific heat for that particular material only depends on number of atoms and molecules, and it does not depend on temperature. So whatever be the temperature, heat capacity of that material will be same. This is what they claimed, and according to them they had given that CV will be 3R. So experimentally, as I told you, it was seen that specific heat capacity for any material, it becomes constant at some temperature, but at low temperature it's less than 3R, or it is decreasing, and at 0 Kelvin it's going to 0 as well. So there this Dulong-Pettit law failed. So at high temperature it's okay, but at low temperature it could not explain why the specific heat capacity of material was going to 0 or decreasing. After this, when quantum mechanics was emerging and concept of photons, which is quantum or packet of light, packet of energy, that concept was emerging. So Einstein, that time we know Planck had given the concept of photons, and Einstein had taken that concept of photon to explain photoelectric effect, and that same concept he applied here, and he took here and he gave another explanation for the for the specific heat capacity behavior, and this model is called Einstein's quantum theory. Under this, what were the assumptions? That atoms in solids or any material that we are talking about, they vibrate with some frequency mu, like harmonic oscillator, and all the atoms or molecules, whatever particles are there, are vibrating independently. So none of them are interacting with each other, and they are vibrating independently. This was the another assumption. Depending on this, it had said that since all the atoms are independent and they are vibrating like harmonic oscillator, so he gave energy of every atom or molecule will be this, where n is an integer. N is an integer, so energies of those cannot be continuous. It has to be discrete values. So this was another thing. That's why this same is coming from quantum mechanics when he explained photoelectric effect, that electrons of any metal cannot absorb any random value of energy. It will only absorb discrete set values of energy, and when it is more than threshold, then it ejects the metal or that material. So the same quantization or discrete value concept Einstein had applied to explain this thermal property, and that's why this was correct thing that he said, that energy is discrete, not continuous. And then all the derivation was assuming that for 3D, if we consider, then each atom will have 3 degrees of freedom. Whenever there is a body, if it's a 0 Kelvin, there is no source of thermal energy. But when we increase its temperature or supply some energy, so the atom, molecule, ion, whatever we have, that is free to vibrate along x, y, or z axis. So it has 3 degrees of freedom in a 3D when we are talking about. And keeping these assumptions that all atoms are vibrating with same frequency and all atoms are independent, and that energy of every atom will be nh nu or nh bar omega if we write it in reduced Planck's constant. The derivation was done. Again, the derivation you can check in the lecture video, and the value of specific heat that he gave was 3R theta E by T square e to the power theta, this is subscript, by T divided by e to the power theta E by T minus 1 whole square, where theta E is h nu by k. This was the final expression that he got after his assumptions. when this expression was checked, because I already told you experimentally we had seen CV varies like this. At higher temperature it becomes constant, but at smaller temperature it goes to zero. So when this expression given by Einstein's quantum theory was checked at very high temperature, if this expression satisfies the experimental result or not. For this, at high temperature, that is when T is very higher than theta E, it was found, when we simplify this, all this you'll find in the derivations in the videos this week. So when at high temperature, it was seen that this expression reduces to, all this simplifies to 1, and finally the expression reduces to 3R. So we can clearly see at high temperature, Einstein's quantum theory was able to explain the experimental behavior. The next was to see what happens at low temperature. At low temperature, that is when T is very small than theta E, and as T tends to 0, from the same expression, when we accordingly take consideration, we get as T approaches 0, CV is 0. So even in this expression, as T goes to 0, CV goes to 0 is correct. But the problem that had happened was for intermediate temperature, because at low temperature, at 0 it is becoming 0, that is correct, but this before 0 and less than this constant, when it becomes constant, the fashion experimentally in between this that we are seeing, experimentally it was seen that in this region CV is actually proportional to TQ. But when we use Einstein's quantum theory derived this expression, we saw that for that intermediate region, CV is actually exponentially depending and not T cube, which experimentally was found. So here it failed to explain the specific heat variation completely. It could explain at higher temperature, it could explain at 0, but not in between. Then another scientist tried to explain this, and another concept was given, and this is called Debye's theory of specific heat capacity. Debye's theory, the assumption here was that, which is very different from Einstein. Einstein said that all atoms are independent, they are not interacting at all. But Debye said that this is not the case. His assumption was every atom is coupled with another atom. This is the assumption we need to consider to explain specific heat capacity, is what he had hypothesized. And the frequency, so one thing was they are not independent. The atoms, molecules, ions are not independent. This was one assumption. Another assumption was that it is because they are not independent, they are connected to each other, they are continuous. This is also another term used. They are continuous elastic body. Okay, this is the same thing, that they are not independent. Another thing was that they are not vibrating independently, and they have modes of oscillation, and the range of oscillation ranges from 0 to some maximum value that is also decided by temperature, Debye temperature concept. So actually we are getting some standing waves for the vibrations happening. The atoms which are vibrating when we are giving energy to the solid, okay, the vibration frequency is between 0 to some maximum frequency, and they are behaving as if standing waves. When these assumptions were taken and he derived it again, so we got Cv is equal to du by dt is equal to 3rd theta by t. This is dBias function, where theta is h mu m by k, where this mu m cube has its expression. So this was checked at high temperature. At high temperature, when this expression was, its validity was checked, then it was seen that for high temperature Cv it was obtained equal to 3R, which was seen experimentally also. Then at low temperature, it was seen that low temperature means this is very small, means this whole expression will tend to infinity, and when this assumption we consider the whole expression is there, when you consider that there, then you will see the expression okay. Anyway, that also you can find in the video, so I'm not going into derivations here. So Cv, from this assumption it was seen Cv was proportional to T cube, which experimentally was also seen. So ultimately this dBias theory was what able to explain how thermal properties, or specifically specific heat of a solid, varies. Experimentally we know, but how to explain it, what's happening exactly. So dBias theory was able to explain it at zero, at higher temperature, and in intermediate as well. So the correct till date, the correct model is that the whole body is vibrating. They are not independent because they are connected to each other. There's a range of frequency in between which they are taking and vibrating with different frequencies depending on their positions in the solid. And with this theory, this Cv, this is especially called dBias T cube law, because this was the only theory, dBias theory, which was able to explain this T cube behavior of specific heat capacity as a function of temperature. And from here the concept of phonon had come. Like in quantum mechanics, especially when black body radiation concept was explained, Planck had said that there is quantum or packet of energy which he had called photon. Same way, in this elastic vibration that is happening in a body when we are supplying energy, there is quantum of or packet of vibrational energy, or a packet of vibration that was named photon. So this was the concept that came from explaining the specific heat capacity behavior. And so these were the three things that was discussed in this week's lecture. And mostly after this is not too much on this topic. And further, more attention is given to the magnetic properties of solids that we'll start discussing next week. So now I think we can start discussing the numerical problems. There is not much related to thermal properties topic, but I have more from semiconductor physics. That was very important, and there are a lot of numericals based on that. So we can start that topic. Okay. So the first question is, the conductivity of semiconductor follows the equation given here, where A is a constant and independent of temperature, Kb is Boltzmann constant, conductivity of germanium is 0.7 per ohm per meter at 0 degree centigrade and 2 per ohm per meter at 20 degrees centigrade. What is the average band gap of germanium? Boltzmann constant value is given. So we need to find out band gap of germanium, and we have been given conductivity. This is one expression, and we can see clearly that conductivity is depending on the temperature. So at different temperature, conductivity value of semiconductor is different. Okay, and here we have been given that conductivity at 0 degree centigrade is 0.7 per ohm per meter, and then at 20 degree centigrade it is 2 per ohm per meter. And from this, if we find out the energy values, then we can find out the, or sorry, if we find out the, substitute these two here, then Eg will be the unknown, everything else will be known, so we'll be able to deduce the value of Eg. So let's put these known thing in this. First thing we need to do here is, these temperatures are given in degree centigrade. For all these numericals, one important thing we need to do is convert these temperatures which are in degree centigrade to Kelvin. So first we'll do that. So 0 degree centigrade, when we convert to Kelvin, we add 273, the number 273. If we go specific, it is 273.15, like 0 degree centigrade is 273.15 Kelvin if we go specific. Otherwise 273 also depends on what is the answer. Our answer should match here. So if we take this as 273, just round off, then 273 Kelvin this will be, and this will be 273 plus 20, that is 293 Kelvin. This step is very important, otherwise the numerical will go wrong. So always in numericals we need to convert temperatures in Kelvin. That is the best thing to do. So when we substitute these two things here, so like let's say this is first situation, second. So for first temperature, there is conductivity is given this. When we substitute, sigma 1 is A e to the power, this is e to the power, this whole expression minus Eg by 2 kBt. Let me write. So the expression that is given is A e to the power minus Eg, and in denominator this kBt is there. Okay, just not to confuse. This is the expression given here. Now sigma 1 will be A e to the power minus Eg by 2 kB, and right now I'll just put the value of, or wait a second, we can do 2 kB. Let's okay, let's say it will be T1. Everything else is constant. Eg also will be the same because it's the property of material. Only thing is, at T1 temperature, conductivity will be different. Other things are all constant. Similarly, for the second situation, the conductivity value is different. A is constant, Eg is value same, 2 kB T2. Okay. Now, if I divide sigma 1 by sigma 2, the value of these conductivities we'll put at the end. Now I am just trying to simplify these expressions. So when I divide these two, A will get cancelled, and in numerator I will be left with this, and in denominator this, e to the power minus Eg by 2 kB T2. Why? Because this A that was there here in both, that will get cancelled. Now I have this. Now we know e to the power x divided by e to the power y. This means e to the power x minus y. This is just power rules. So with that logic, this will become e to the power minus Eg by 2 kBt, and this is negative, so when it will come to numerator it will become positive. This is T1 plus Eg divided by 2 kB T2. Okay, So what we had, sigma 1 by sigma 2 is equal to, I'll write it in simplified. I can take common Eg and 2 kb I can take out common, right? E to the power Eg divided by, this G is subscript, 2 kb, and inside I will have minus 1 over T1 plus 1 over T2, minus 1 over T1 plus 1 over T2. Okay. I need to finally find out Eg. So I need to get rid of this e to the power. I want to get rid of this exponent. So one way is to take natural log on both sides. When I do that, okay, natural log of e to the power Eg over 2 kb, and this also I'll just swap them right and left, so it will be 1 over T2 minus 1 over T1. Like there's nothing different I've done, they are getting added, so I've just written this first and this later. Now another interesting thing, if you remember the property, natural log of e to the power x, anything on e to the power, when we are taking natural log, it becomes this. So natural log of e to the power x is equal to x. And that is what I told, that we want to get rid of this e so that we can conveniently calculate this Eg value. So now we are doing this. So this, let's leave it. The natural log of e to the power, this is there in the exponent. So this all we will get here. Eg divided by 2 kb and 1 over T2 minus 1 over T1. Now we can substitute values and find out. So another property of whenever we take natural log or log to the power 10, log to the base 10 also, is that when we have something like this, we can write like log of a minus log of b. Okay, so here also it will be log of sigma 1 minus log of sigma 2. Now when we substitute, okay, we can do some little more rearranging to get Eg. Let's see, if I send this denominator to this side, it will be 2 kb sigma 1 minus sigma 2. Okay, and this side I'll be left with Eg, and this T1 minus T2, right? So it will be T1 minus T2 divided by T2 T1, and this whole thing, if I send on opposite side, it will be 2 kb natural log of sigma 1 minus natural log of sigma 2. Either you can substitute in the beginning and do everything, or you can simplify expression like this and then substitute these known values at the end. Either way is fine. Then this will be T1 minus T2, and in multiplication 2 T2 T1. This is the value of Eg. Now if we substitute, Eg is equal to 2 kb, 2 and kb, Boltzmann constant. It is 1.38 times 10 to the power minus 23 joule per Kelvin. 1.38 times 10 to the power minus 23 joule per Kelvin. Then we have this natural log of sigma 1 minus natural log of sigma 2. Natural log of sigma 1. Sigma 1 was 0.7 minus natural log of sigma 2. Sigma 2 was, for second situation, it was 2 per ohm per meter. Natural log of 2. And next is T2 times T1. T2 T1. 1 is temperature, 293 Kelvin multiplied by 273 Kelvin. 293 multiplied by 273. All this divided by T1 minus T2. That means 273 minus 293. When we solve all this, let's do this. I use my calculator. So natural log of 0.7. So let me just tell you, natural log of 0.7 is minus 0.3567. Like in exam also you will have digital calculator, so you don't need to remember or anything. You can just use the calculator, and I'm telling you these values using calculator right now. So natural log of 2 will be 0.6931 or 32, because there are a lot of values. And after this, when we this minus 0.3567 minus 0.6932, this will become minus 0.3568, and this multiplication, 293 multiplied by 273 is 79989. This was what was the in bracket here, and this thing will be 2 times 1.38 is 2.76, and this power is still there, 10 to the power minus 23. These are in multiplication, so order doesn't matter, of course. And in division, 273 minus 293 means minus 20. This here is minus, so ultimately our answer is going to be positive, so no problem there. And further doing the calculation, 2.76 multiplied by 0.3568 multiplied by 79989 divided by 20. Answer will be, wait, I have to consider this, but apart from that, the answer will be 3938.5304 multiplied by 10 to the power minus 23. This will be in joules. Okay. All this will be in, let me just check once. Well, the answer is just check. Oh, sorry. 2.76 multiplied by 0.3568 multiplied by 79989 divided by 20. Yeah, that was correct. And then ultimately the answers options here are in electron volt, and we know joule to we know that 1 electron volt is 1.6 into 10 to the power minus 19 joules. So to convert it into joule, we'll divide by this, and thus we'll get the answer of 0.72 electron volt. And A will be the correct answer. Okay. Next question is, find out the conductivity. Conductivity we need to find out of pure silicon at room temperature. As we know, conductivity depends on the temperature. So here we need to find out the value of conductivity at room temperature, and the value is given 300 Kelvin. This is the assumption we do, even if 300 Kelvin is not written. When it's usually referred to as room temperature, we take 300 Kelvin, and to convert from degree centigrade, we add 273. So if we subtract here, you will see this is 27 degrees centigrade. 300 Kelvin correspond to 27 degrees centigrade. This is usually considered room temperature. It, of course, actual room temperature can even go 30, 40, but this is until any other value is given, mentioned in the question, we can always take 300 Kelvin as the room temperature value. Okay. So further, mobility of electron is given, mobility of hole is given, and intrinsic charge carrier concentration is given. Now we have been given pure silicon, okay, and we need to find out its conductivity at room temperature. This formula for intrinsic, it's pure, so for intrinsic conductivity of silicon, the conductivity formula will be, this is the intrinsic charge carrier concentration, this is the charge of the carrier, and because there will be equal number of electrons and equal number of holes, so mu h plus mu n, because it's pure silicon, there is no doping, so number of electrons, number of holes, same. This is the formula for electron conductivity, and it's okay. So although we didn't need it here, that actual anything to do with temperature, but still just keep in mind that if we need to use the value of temperature and nothing else is given, then 300 Kelvin is the room temperature considered. But here for this formula we didn't need this, so just we'll put the values in this formula. Intrinsic charge carrier concentration value 1.5 times 10 to the power 16 per meter cube. Charge of electron will be 1.6 times 10 to the power minus 19, and this is mobility of electron and mobility of hole, that is 0.13 and 0.05. After adding all this, 0.13 plus 0.05 is 0.18. This is 0.18, and multiplying this, 1.5 times 1.6 is 2.4. 4 multiplied by 10 to the power 16 minus 19 times this. So this will be 2.4 times 0.18 is 0.432, and in the power it will be minus 3. So if I bring the decimal to the right, then it will become 4.32 10 to the power minus 4, and the unit will be, because it's conductivity, so unit will be per ohm per meter. So the correct answer is this, B. Next question, calculate the resistance of a bar of pure silicon of length is given, cross sectional area is given. We have to find out the resistance at 300 Kelvin. Okay, so we know we have formula to find out resistivity or conductivity, and we can take reciprocal and we'll get resistivity. And here we have been asked resistance. Now we know what is the relation between resistance and resistivity of any material. It's given by rho L by A. We need to ultimately find out resistance in this question, and for conductivity we have this formula, the same formula that we use, mobility. It relates mobility, charge of the carrier, and charge carrier concentration. From this we will be able to find out the conductivity. Reciprocal of it will give us resistivity, and length of the material is given, its cross-sectional area is given, so we can find out resistance. So let's do this. Intrinsic charge carrier concentration value is this, 2 times 10 to the power 16 per meter cube. Only just keep in mind all these should be in SI unit, like this is not in SI unit, this is not in SI unit. So when we are using them in numericals, we should convert. Other things all are in SI unit, so fine. So this is okay. Now again, charge 1.6 times 10 to the power minus 19, and mobility is 0.14 plus 0.07. Then we'll calculate this. 0.14 plus 0.07, that will be 0.21 multiplied by 2 and 1.6, 0.672 multiplied by 10 to the power 16 minus 19. This will be per ohm per meter because it's conductivity. Okay, we can rewrite it like this. This will be 10 to the power minus 3, and we can write like this. It will be 10 to the power minus 4 per ohm per meter. Okay, now what we need to find out? Resistivity, which is inverse of this conductivity. So this will be 1 over this. Now 1 divided by 6.72 will be 0.1488, and this will be 10 to the power 4 ohm meter. Now it's resistivity. This will be the resistivity, and ultimately we need to find out resistance. Okay, and L is given to be 1 centimeter, and area, cross-sectional area, is 1 millimeter square. And as I said, we should convert everything into SI unit because our final answer is all in SI unit. So 1 centimeter when converted to 1 meter, 1 meter is 100 centimeters. So this will be 10 to the power minus 2 meters, and 1 meter has 10 to the power 3 millimeter. Yes, and this is millimeter square. That means 10 to the power minus 3 square meter square. That means 10 to the power minus 6 meter square. So here when we substitute, the resistivity is 0.1488. 0.1488 times 10 to the power 4 ohm meter multiplied by length, which is 10 to the power minus 2, divided by area, which is 10 to the power minus 6 meter square. Finally we'll get 0.1488. Wait, length was 1, magnitudes were 1. Okay, so it's okay. And 10 to the power 4, and here it will be 10 to the power minus 2, and this when will come to numerator, it will be 10 to the power plus 6. So plus 6. 6 minus 2 means 4. That means 88 times 10 to the power 4 plus 4. That means 10 to the power 8. Okay, the answer is in mega ohm. Mega means, this means mega, and this means 10 to the power 6. Okay, so this expression is what? 0.1488 10 to the power 8. If I want to change it to mega, then I need to drop 100 from this, right? That means 2 decimal places will shift, and it will be 14.88 10 to the power 6 ohm. Now it's resistance, so everything is in ohm, and this I can write it as 14.88. This 10 to the power 6 is mega ohm. 14.88 is the correct answer. Next question. Find the conductivity of a So we find the conductivity of p-type germanium crystal, which is doped with acceptor atoms. Acceptor atoms means they accept the electrons. So they are p-type, I mean trivalent atoms. They accept the electrons. So acceptor atoms concentration is this, and all the acceptor atoms are active. Mobility of hole in the crystal is this. It's a p-type germanium crystal. Okay, that means the majority charge carrier will be it's p-type germanium crystal. That means majority hole is there. Why? Because when we doped with acceptor atoms accepts electrons. So when we doped acceptor atoms, they had more holes. They took the electrons, and now the majority charge carrier in this p-type germanium crystal is holes. That means number of holes is very large than number of electrons in this p-type semiconductor. That means we can say that number of holes is equal to number of acceptor atoms, and that is given to be 2 times 10 to the power 23, because the number of electrons, as I said, when we introduce acceptor atoms, they depending on how many we are accepting, that many they will accept the electron, and thus extra positive charge will remain in the material, that is extra hole will remain. So if I'm adding one acceptor atom to the material, it will take one electron. That means it will accept one electron and I'll get one hole. If I'll introduce n number of, then they will accept n electrons and I will be left with n number of holes. So that's why the concentration of hole will be equal to the number of acceptor atoms I am doping. We can say that equal number of acceptor atoms is equal to equal number of holes. I hope this is clear. Almost we say, because maybe sometime defects and other things happen, but still we can take this assumption as equal. So this will be the concentration of holes indirectly. We were told the concentration of acceptor atoms and we could reduce the number of holes. Okay, now we need to find out conductivity. Formula we know, mobility is given, concentration we got. So now we can find out the conductivity. So the formula will be, like we know the formula here, it will be the concentration of hole, because hole is the majority charge carrier. So only hole we care, we don't care about the negative charge carrier, which is electron. And thus our expression reduces mobility of holes and the charge of holes. So concentration of holes was 2 times 10 to the power 23. 2 times 10 to the power 23. Mobility of hole is given 0.19, 0.19, and charge we know 1.6 times 10 to the power minus 19. And this, since this is conductivity, the unit will be per ohm per meter. And when we do the calculation, 2 times 0.19 times 1.6, this will be 0.608, and the powers 10 to the power 23 minus 19 per ohm per meter. This will be 0.608 and 10 to the power 4 per ohm per meter. Okay, the answers are not in powers, so we'll just write it and rewrite this. So to remove this, it will become 6080 per ohm per meter. This is the conductivity. So A is the correct answer. Next question. Calculate the concentration. We have to calculate the concentration of acceptor atoms that have to be added to an intrinsic semiconductor to produce a p-type semiconductor. So first, what this portion of the question is saying is that we have to find out the concentration of acceptor atoms. So acceptor atoms were added to intrinsic semiconductor. Acceptor atoms means they have holes, that means they are trivalent. And when we added them, let's say Na number of acceptor atoms we added to this intrinsic, and now they will accept the electrons. How many? The number of doping we are doing, the same number of electrons they will accept, and thus we will be left with holes, and thus this intrinsic or this pure semiconductor will turn to p-type semiconductor, same thing. And so what information, so I mean this is what is happening. We are adding trivalent atoms or acceptor atoms which will accept the electrons from this intrinsic semiconductor, and we will be left with holes in this, and thus it will become extrinsic p-type semiconductor. This is what is happening in this situation. Now we have to find out how many atoms are required to add so that this p-type semiconductor's conductivity will become 0.05 per ohm per meter. How many we should acceptor atoms or dopings or dopants should we add so that this extrinsic semiconductor's conductivity, which will be of course because of the holes now, will become 0.05. This is the situation given, and mobility of holes value is given. Consider all acceptor atoms are active. So this is also thing like because of defect or something, maybe I'm adding 2 and only 1 is active or something. But here we have to just accept that whatever number of acceptor atoms I'm adding, all are accepting electrons from my material. So the number of acceptor atoms I'm adding, the same number of holes I will get in my material. I hope this is clear. And because of that, this should be clear, the number of atoms that I'm adding, the same number of holes I will have in my material. And now I need, using the conductivity expression, conductivity is because of hole here, and the expression we know, the concentration of hole and mobility of hole and charge. Now as I said, the number of acceptor atoms I will add, the same number of holes will remain in this material. So using this, anyway I need to find out the concentration of acceptor atoms. This is what I need to find out, and this I can get from this formula, and then that will be equal to number of acceptor atoms. I hope this is clear. If this statement is not clear, you can tell me, I'll explain this again. And if it's clear, we can proceed. And sigma h we know, which is 0.05. NH we need to find out. Mu n, mobility is given 0.4, and charge 1.6 times 10 to the power minus 19. When we do this, or I can write this on one side, on another side will be 0.05 divided by all this. 0.05 divided by 0.4, and the charge of the carrier 10 to the power minus 19. So this will become 0.05 divided by 0.4 divided by 1.6. So it will be 0.0125, and this will be 10 to the power 19. This is the answer. Okay, the answers are in, let me rewrite this. So this will be 1.25 10 to the power 17 per meter cube. 1.6. I make some mistake. Just 0.05 divided by zero point 0.4 divided by 1.6. Okay, I made mistake here. It should be 0.0781. Okay, that. So mistake in calculation, it should be 0.0781, and then when I take care of the power, it will be 7.81 multiplied by 10 to the power 17 per meter cube. 7.8 10 to the power 17 per meter cube. This is because just now we found out number of hole, and I explained you in the beginning that number of hole is equal to the number of acceptor atoms I had added to my pure semiconductor. So number of or concentration of acceptor atoms is, yeah, I'm using number of, but actually it's concentration. The values here is per meter cube. So not number per unit volume, that is concentration. Okay. Oh, sorry. This is the correct answer, option C. Okay. Next question. The energy gap in germanium. Okay, energy gap value is given in germanium to be 0.75 electron volt. Compare the intrinsic conductivity of germanium at 27 degrees centigrade and 57 degrees centigrade, assuming the conductivity of intrinsic semiconductor follows this equation. Okay, then at 27 degrees centigrade, that means in Kelvin, we need to first convert it to Kelvin. That means in Kelvin, this will be 300 Kelvin after adding 273, right? 273 when we add, yeah, it will be 300 Kelvin. And the second is 57 degrees centigrade. That means it will be 273 plus 57, that is 330 Kelvin. These two conditions, if I substitute here, energy gap value Eg is given, then I'll be able to find out what they mean is I have to compare and everything is known. I think like how much bigger is the conductivity as 27 degrees centigrade than 57 degrees centigrade, vice versa, I think. So we can find out ratio, it seems here. So let's substitute the expression of dependence of conductivity for germanium. The expression is this, that the conductivity is, this is some constant, T to the power 3 by 2 e to the power minus Eg divided by 2 kBt. This is the expression. Now for first case, sigma 1 will be, C is just constant, T1 to the power 3 by 2, e to the power minus Eg is anyway same, 2 kB T1. This is for first case. For second case, sigma 2, another conductivity, and this is constant, T2 3 by 2 e to the power minus Eg by 2 kB T2. So like this, two formulas only we have been using. One, this is already given in the question. Just we have to modify it and think how we can find out the unknown. So this is second. We have to compare. So let's take 1 by 2. Let's divide equation 1 by 2. When we do this, we'll get sigma 1 by sigma 2, which is equal to, again the C will be cancelled and we'll be left with this. So T1 to the power 3 by 2 e to the power minus Eg by 2 kB T1 minus Eg by 2 kB T1, and in numerator we have T2 to the power 3 by 2 and e to the power minus Eg by 2 kB T2. Okay, how we can write this? Because I told earlier also e to the power x divided by e to the power y is e to the power x minus y. So this portion will become e to the power minus eg by 2 kBt1, and this when will go to numerator it will be plus. So plus eg divided by 2 kBt2. Okay, and then this will be simply t1 by t2. We can write like this because both have same power, so we can write like this, and then multiplication, this whole thing is in power. This is sigma 1 over sigma 2. Okay, now when we substitute the values, or we can further simplify this, we can take out eg by 2 kb, we can take them out, t1 by t2 to the power 3 by 2 multiplied by e to the power eg by eg by 2 kb, we have taken common, and then minus 1 over t1 plus 1 over t2. When we substitute, t1 was 300 Kelvin, t2 was 330 Kelvin, all this to the power 3 by 2, and this e to the power eg is given, which is 0.75 electron volt. Now electron volt we need to change to joules, and 1 electron volt, just to recall, is 1.6 times 10 to the power minus 19 joules. Okay, 0.75 electron volt means 0.75 multiplied by 1.6 times 10 to the power minus 19. In division we have 2 and kb. kb is 1.38 times 10 to the power minus 23 joule per Kelvin. And what we are left with? Minus 1 over t1. t1 is 300 plus t2 is 330. When we solve all this, let's see what we get. 300 divided by 330 to the power 3 by 2. This will be 0.8668, and e to the power, when we'll solve all this, so divided by 0.75, 1.6, 15, divided by 1.38, I'm getting e to the power this will be in minus, and minus 1.3175, 10 to the power minus 4 minus 19. Okay, first let me solve this. 23 minus 19, 4, and from this I'm getting, okay, so powers will be cancelled and I'll be left with this. Now e to the power minus 1.3175. Okay, further this will be, so sigma 1 by sigma 2 will be 0.8668 multiplied by this e to the power, all this will be 0.2678, 0.8668. Answer will be 0.2321. This will be the ratio of the conductivities. That what this means is sigma 1 is 0.2321 times sigma 2, and the conductivity at 330 Kelvin is more for this germanium, because for semiconductors we know with increase in temperature the conductivity increases because more and more number of electrons or holes are readily available for conduction, and that is what we are seeing, that conductivity 2 is more than conductivity 1, and the ratio is 0.2321. So first only up to 2 decimal digit if we have to take, then round off and we'll get this as the correct answer. So just take care of these. It may seem complicated, but you may solve it step by step, like first do this, then do this. Anyway, you have calculator to solve all this. Just take care of signs, exponents, and you'll be able to get the correct answer. Okay, next question. Silicon is doped with boron. Now boron is a trivalent atom. It is an acceptor atom. It is from group 13. Silicon is doped with boron, and the concentration of boron atoms, acceptor, they are acceptor atoms. So concentration of acceptor atom is given to me 4 times 10 to the power 26 per meter cube. Assuming intrinsic concentration of silicon is this 1.5 times 10 to the power 16 per meter cube, find the position of Fermi level of doped semiconductor with respect to intrinsic Fermi level. So when the semiconductor is undoped, then conduction band, valence band, and Fermi energy is exactly in between. But when we do doping, and depending on what kind of doping we are doing, either hole can increase, number of holes, hole concentration, or number of electron concentration can increase, and accordingly the Fermi energy level will go up or down. So here what is given is we have to find the position of Fermi level when we are after doping, and the intrinsic Fermi level with respect to intrinsic Fermi level at room temperature. Okay, so this is clear that acceptor atom concentration is this, intrinsic concentration of silicon is this value, and we have to find out how much. So earlier the energy, Fermi energy was exactly in between, sorry, not energy band, Fermi energy was exactly in between. Now it will shift either up or down. So how much is the shift we need to find out. That means if earlier it was, let's say, intrinsic Fermi energy level was this, then how much this new energy level is shifting, that we'll find out from energy level expression. When we take this is the formula, where P is the number of holes. So holes will be as number of, equal to number of acceptor atom concentration. That means KBT natural log number of acceptor atom divided by intrinsic concentration. This, when we substitute the value, KB is 1.38 given 10 to the power minus 23. Temperature, it's talking about room temperature 300 Kelvin, and natural log of Na is 4 times 10 to the power 26, and Ni is 1.5 10 to the power 16 per meter cube. Both are in meter cube, so that is fine. So 4 divided by 1.5 is 2.6, and the power 26 minus 16 means 10. 2.6 times 10 to the power 6. This, oh sorry, First, let me multiply this. 1.38 times 300 is 414, 10 to the power minus 23, and natural log of this will be 4 divided by 1.5, that is 2.67, and these powers will be 10 to the power 26 minus 16 means 10 to the power 10. Let's take it to the next page. This will be 414 times 10 to the power minus 23 natural log of a multiplied by b means natural log of a plus natural log of b of 2.67 natural log of 10 to the power 10. Okay. And further, when we will do this, natural log of 2.67 is natural log. So let me just able to find out natural log. So we're not able to find out natural log where I lost in my. Okay, yeah, found. Sorry. There are too many functions in my calculator, I got confused where to look for it. Natural log of 2.67 is 0.9821 plus natural log of 10 to the power 10 means 10 natural log of 10. So natural log of 10 is natural log of 10 is 2.3 multiplied by 10, that means 23. 23 plus this means 23.9821. Power, let me write this side, and 414. When you multiply all this, 3.9821. We'll get answer 7.078 into 10 to the power minus 20. This will be in Joule because we are finding out the difference. And when we'll convert, because the answers are in electron volt, so we'll convert electron volt, we'll get 0.44 electron volt. This is the shift, and since we subtracted from Fermi intrinsic to now, that means it is below than earlier. That means 0.44 electron volt below to the intrinsic Fermi level. If it would have been negative, means it's going up. Next question is, a sample of germanium is doped to the extent of 10 to the power 20 donor atoms per meter cube. So donor atoms per meter cube is 10 to the power 20 per meter cube, and acceptor atoms is 5 times 10 to the power 20 to the power 19 per meter cube. At 300 Kelvin, resistivity of intrinsic germanium is 0.6 per ohm per meter, or resistivity, so ohm meter. If the applied electric field is 200 volt per meter, find the total conduction current density. Assume the ratio of hole mobility to electron mobility is this. Okay, let's do it step by step. So one thing is, this formula we have tells electron concentration, because there is, in this doped, there will be holes also and electrons also. So concentration of electrons in this semiconductor will depend on number of donor atoms and number of acceptor atoms. We are adding both donor atoms and acceptor atoms here. Okay, so the net will be, there will be holes also, there will be electrons also. And here if you focus, actually, if this is 10 to the power 20, if I make this also, then this will be 0.5 10 to the power 20 per meter cube. That means I'm adding more donor atom than acceptor atom. This also we can see from here, but the formula for number of electron concentration here, Nd minus Na divided by 2 plus, this is the formula you can find in the derivations, 2 plus intrinsic carrier concentration. Using this formula, when we substitute the values, now let's do a little faster because we have few more questions to do. Okay. So this values, when we substitute 10 to the power 20 minus 0.5, right, just to make the power same, 0.5 10 to the power 20 divided by 2 plus this is again 1 minus 0.5, that means 0.5 divided by 2, right? This is, I'm taking 10 to the power 20 outside, so it will be 1 minus 0.5, that means 0.5 divided by 2 whole square, and 10 to the power 20 whole square, that means 40. And intrinsic carrier concentration, which is this, 2.5 times 10 to the power 19 per meter cube. When we solve this will be 1 minus 0.5 means 0.5 divided by 2, 10 to the power 20, plus, when we solve all this, we will get 3.5 times 10 to the power 19. If you do this, you will get, this total will be 6 times 10 to the power 19 per meter cube. This is electron concentration. Now hole concentration, we can call P naught will be N naught square by N naught point 5, because number of donor atoms were more, number of holes were more, number of electrons were more. For number of holes, we can just use this. To the power 19 per meter cube. Conductivity for intrinsic semiconductor will be 1 over 0.6, 1 over 0.6 per ohm per meter, which is equal to this formula. Both holes and electrons are there. Conductivity is given, and this is the formula. So the mobility we will get, hole and electron will be 0.6 times 1.6 times 10 to the power minus 19, 2.5 times 10 to the power 19. When we solve all this, we'll get 0.42 meter square per second. Now, as I told you already, holes were half of number of electrons there, right? or number of electrons was 2 times mobility, sorry, not holes. Equal to 3h, and this one is 0.42. So mobility is 0.42 divided by 3, that is 0.14 meter square volt second, and mobility for electrons will be 0.42 minus 0.14 is 0.28 square per volt second. Total conduction current density for this situation of semiconductor will be E. This is electron concentration, its mobility plus the charge, and hole concentration and its mobility, and the electric field that we are applying, which was 200 volts per meter. 1.6 times 10 to the power minus 19 hole concentration, 6 times 10 to the power 19 divided by 0.28 plus 10 to the power 19 multiplied by 0.14, and the electric field is 200. When we do all this, substitute, the current density will become 1.6, 6 times 0.28 plus 0.14 times 200, and after solving all this, 582.4 ampere per meter square change to will be the correct answer. And the answer is in this ampere per centimeter square. So changing to centimeter, 1 meter is 10 to the power 2 centimeters. So accordingly 582, sorry, 0.058 ampere per centimeter square will be the correct answer. Option A is the correct. Okay, next question. In an intrinsic semiconductor, effective mass of electron is 0.09 MeV. MeV is the rest mass of electron, which is 9.1 10 to the power minus 31 kg. Okay. And we have been whole. Okay, this is for electron. Effective mass of hole is 0.4 E times Me. Me is the electron rest mass, that is this. This is Me. Calculate intrinsic carrier concentration at 300 Kelvin, where energy gap is given and all other things are given. So formula we have based on effective masses. The formula for intrinsic carrier concentration is this: 2 pi kBT divided by h square to the power 3 by 2 effective mass of electron, effective mass of hole to the power 3 by 4 e to the power minus Eg by 2 kBT. Substituting these values, 2 and pi and kb is 1.38, 10 to the power minus 23, temperature is 300, to the power 3 by 2, h square, h is 6.62 times 10 to the power minus 34 whole square, and now all this 0.09 times ME, right? ME, that is 9.1, 10 to the power minus 31 kg. I'll write all together. MH is 0.4, and now that is also times ME. So ME I'll take together 31 and square of this, right, and power 3 by 4, and now I'm left with e to the power minus Eg by 2 kVt. E to the power minus Eg is given to be 0.7 electron volt. Okay, I'll go to next page. So e to the power minus Eg is 0.7 electron volt. We need to change it into joules. So 1.6 times 10 to the power minus 19. Okay, this we done with Eg. Now in division we have 2 kVt. 2 kV is 1.38 times 10 to the power minus 23 joule per Kelvin, and T is 300. Okay, that's a very big expression. This is E I have written on, wait a second, on next page. So after solving all this, because I have few more questions, I'm skipping solving. You guys can see and you will get the answer. We will get, for solving, one more step I'm giving. After solving this first bracket, you get 2.89 times 10 to the power 70, and after solving the second bracket we will get 7.17 times 10 to the power minus 47, and the exponent when we will solve we will get 1.33 times 10 to the power minus 6. Okay, and then taking product of all this we will get 27.5 times 10 to the power 17 per meter cube as intrinsic carrier concentration. Okay, and answer, okay, to match the answer we will rewrite this as 2.7 10 to the power 18 per meter cube. The answer is option A. So these small, all the things that were derived from derivations that were done in the lectures, we need to keep those formulas in mind. Another question is, at a given temperature, a semiconductor with intrinsic carrier concentration is doped with donor dopant of concentration. Okay, they have written small, so small, 10 to the power 26 per meter cube. If the temperature remains the same, calculate the concentration of whole. Intrinsic carrier concentration is given, dopant is given, so we need to find out concentration of whole. Concentration of whole, the formula is Nd by 2 plus Nd by 2 whole square plus Mi square. We substitute, it will be 10 to the power 26 by 2 plus 1 10 to the power 26 divided by 2 whole square plus 10 to the power 16 whole square will be 10 to the power 26 square. All this one will solve, will be 10 to the power 26 per meter cube is the sorry, this was electron concentration and not electron concentration. Okay. Now whole concentration is will be Mi square by M naught, which will be 10 to the power 16 square divided by 10 to the power 26. This will give us 10 to the power 6 per meter cube. So whole concentration will be, for whole concentration we need to find out electron concentration, and electron concentration we find out like this. Okay, so the correct answer is answer B. If we have time, I have 1 minute. Like I have one question where it was related to Debye theory, and in the question we were asked to calculate the Debye temperature. Sorry, the question is missing here. But in this question, we were asked to calculate Debye temperature, and we were given atomic weight of gold, which is 197 atomic weight. Density was given, which was 1.9 times 10 to the power 4 kg per meter cube, and Vs velocity was given 2100 meter per second of the Rask wave. So we had to calculate Debye temperature. Now we know Debye temperature, this value this is given by this expression k wave vector Boltzmann constant 12 pi is also volume to the power 1 by 3. This was again from the derivation. I'm like just telling you, sorry I missed to put the question, but this was the question, these were the given things, and we had to calculate Debye temperature. So here after substituting H, we know the value. Let me just write 6.62 10 to the power minus 34. So Vs is given 2100 meter per second, and Boltzmann constant 1.38 times 10 to the power minus 23 joule per Kelvin. To calculate Avogadro, this is Avogadro's number, Na 6.02 into 10 to the power 26. Why? Because we are converting it into kg. Otherwise, 1 gram has 6.023 into 10 to the power 23 moles. Here, we will convert it into kg, then it will be 10 to the power 26. This we had done several earlier also, so I hope this is clear. And then in denominator we have 12 times pi times volume. For volume, we know mass, when we divide by density, we will get volume. So that expression, when you substitute, answer will be 240 and to the power 1 by 3. Answer will be 240 Kelvin. Okay. So this is another way you need to keep in mind these formulas, so that you can just put the values and find out the answer. So this was one question. Okay, so this was all for this. I hope these questions are clear. Most of them we solved in real time, one or two at the end because we are short on time. So I just gave you the final answers. You can try. If you have question, you can ask either in comment in the discussion group or in the next class also. So for now, let's end the session.